Hi everyone, Mrs. V here, and today we are going to look at our first video in the chemical properties of alcohols, in which we look at the reaction between alcohols and sodium metal. This is an important way to test for the presence of a hydroxyl group. So let's cut to our PowerPoint and learn some more. Sodium test for hydroxyl groups will occur for any molecule that contains a hydroxyl group. And this is a really important thing to realize about functional group chemistry, that when we look at the reactions for a particular functional group, it is the functional group that is reacting. The rest of the molecule is a bit of a passenger really in the process. So any molecule containing the functional group is going to actually undergo a reaction. A positive test with sodium for an alcohol will cause bubbles of hydrogen gas to be given off, and that hydrogen gas can be tested using the pop test. All right, let's continue. So here I have a video of the sodium test being performed. So let's have a bit of a look here. We have here ethanol. So there's some ethanol in the test tube, and we're going to add some pieces of sodium to that ethanol in the test tube, and immediately you can see bubbles of hydrogen gas being produced. This is very similar to the reaction that occurs when you put sodium in water. Now I want you to note here that the sodium is more dense than the ethanol. The sodium is actually sinking to the bottom of the test tube, showing that it has a greater density. That's very different to sodium and water. So the hydrogen gas that's produced can be collected and tested using the pop test. So we can confirm the presence of a hydroxyl group by the production of that hydrogen gas. This reaction occurs for any molecule that has a hydroxyl group, even water. If we consider water, we write water out as HOH. We can see that water can be considered to have a hydroxyl group as well. And of course, sodium reacts with water. So in this, we see some sodium being placed in a beaker of water, and immediately you can see the sodium fizzing around on the surface. In fact, the heat produced has become so great that the hydrogen gas being produced is igniting. You see the characteristic yellow sodium flame color there. So that reaction is being caused by the presence of the hydroxyl group. So it wouldn't matter if you had water, an alcohol, a carboxylic acid. It wouldn't matter if the hydroxyl group was on a super large molecule. Maybe you've got a molecule like this one. Maybe you've got several ring shapes joined together. These molecules do actually exist, by the way. You might have some long chain here and a hydroxyl group. It doesn't matter how big the molecule is, you still have a hydroxyl group, so this will still react with the sodium. And that's always going to produce hydrogen gas, which you can test with a pop test. So primary, secondary, and tertiary alcohols will all react. It doesn't matter if you have the hydroxyl group in any configuration in an alcohol. Carboxylic acids also have hydroxyl groups. Water does. There's also phenols. Here, this is phenol when you have a hydroxyl group attached to a benzene ring. All of those will react because it's not the whole molecule that's reacting here, it's just the hydroxyl group. So as long as you've got a hydroxyl group, you've got that reaction. So let's have a look at how this reaction occurs. So we know the reaction of water, H2O with sodium, produces sodium hydroxide. and hydrogen gas. We've seen this reaction probably since we were in middle school. Very similar though, alcohols are simply an alkyl group. And by alkyl group, I mean a methyl, ethyl, propyl, butyl, etc., attached to a hydroxyl group. So instead of getting sodium hydroxide being produced, as you do with water, you're going to get sodium alkoxide. So that could be methoxide, ethoxide, propoxide, etc. Okay, so this R group is just representing some alkyl group. It's really just the rest of the molecule that's not the OH group. Right, so the way this occurs, so I'm going to look at ethanol as an example. So ethanol is CH3, CH2 with a hydroxyl group. Now, the way this reaction occurs when you add sodium is that the electrons in the bond that the oxygen's making with the hydrogen are both shifted onto the oxygen. Now, that means the oxygen has contributed one electron to that bond and the hydrogen's contributed one, but both electrons are going onto the oxygen. So that means that that oxygen is going to get a negative charge. So in the products, we're going to have the ethoxide ion. So this is going to have a negative charge. And the hydrogen is coming off as H+. And that means that what we're having here is that so the hydrogen comes off without its electron as H+. So the alcohol is donating H+. So the alcohol is acting as an acid by the Bronsted-Lowry definition. And what happens then is the sodium metal is going to donate its one electron to the hydrogen, which means that the sodium is going to produce Na+, which will be attracted to the ethoxide ion, and we're going to get half a mole of hydrogen gas produced as well. The name of our organic product is sodium ethoxide. Now this will react with, this reaction will occur for carboxylic acids as well. Let's have a look at vinegar, which is ethanoic acid. Common name acetic acid. And this reaction will occur with the hydroxyl group on ethanoic acid as well. Actually, I might write that out. A full bond. So if we add sodium here, then our mechanism is that the two electrons in this bond will go to the oxygen. The hydrogen comes off as H+, and we will produce, when it's a carboxylic acid, it produces an alkanoate ion. So that is the ethanoate ion. And the sodium will donate its electron to the hydrogen, So we'll have Na plus attracted to the ethanoate ion, making sodium ethanoate. And again, we'll get our half a mole of hydrogen gas. All right, time for you to take a turn. Let's have a look at these two examples. I want you to pause the video. I want you to write an equation for the reaction of methanol with sodium, and I want you to name the organic product. Come back when you're done, and we'll go through the answer. Okay, methanol. Methanol is CH3OH. We're adding sodium, and you'll remember that the electrons in this bond here are both going onto the oxygen, and that the sodium is going to donate an electron to the hydrogen. So we end up with the methoxide ion with the sodium ion, so that's sodium methoxide. And of course, not forgetting our half a mole of hydrogen gas that's produced from that reaction. Okay, slightly more complicated, but remember, it's just the reaction of the hydroxyl group. It does not matter what it's connected to. Have a go at 2-methyl-butan-2-ol. Okay, come back for the answer when you're done. All right, 2-methyl-butan-2-ol, what is it? There it is. Oh, I keep forgetting to write that bond out so that I can do the mechanism. Love a good mechanism. Okay, so we're reacting this with sodium, and both electrons in that bond are going to the oxygen. So we have a double-headed arrow there. The sodium is going to give its electron to that H plus to make hydrogen gas. So we end up with this ion here, or this compound here, and half a mole of hydrogen gas. Now, what is that called? It's come from 2-methyl-butan-2-ol. So this is sodium 2-methyl-but-2-oxide. So quite clear, really. You'll notice that we just write the sodium ion wherever the negative ion is on the molecule. And for organic compounds, we leave the charges in when we write the formula for the ionic compound. Okay, that's all for today. I will see you guys in the next video.